And we're recording. So, okay, welcome to Numerical Analysis 2, Math 461 if you're an undergrad, or 561 if you're a grad student. So, never like the first day of class because you're just trying to get a bunch of little things out of the way, pretty much. So I'll try to do that quickly. So here, let me get my notes in order. All right. So I'm passing around syllabus and schedule. And while that's going on, we'll see who's here. First for undergrads. Okay, Reina. Else? Okay. It's a little hidden back there. Okay, Karina. All right, Cooksey, Kelsey. Okay. Keys. Yeah. Okay. Alrighty. Carell. That's strange. Okay. Timber. Yep. Okay. Menandar. Okay. Rester. All right. Walker. Yep. Okay. All right. That's all the undergrad. And then the grad students. Okay. I'm not going to pronounce these correctly, so I'm just going to go phonetically. Akampong. How do I pronounce that? Okay. All right. I should have gone more phonetically then. Now, which name do you go by? Kwesi. Okay. All right. I can handle that. Okay. All right. Good. Lionel. Okay. Good. Amuzu, or that's what? Yeah. Okay. All right. Good. All right. Okay. Tavish here. Kristen. Yep. Okay. And then I know most of you, but it's like, where in the room are you? Okay. Treasurer's remote. Cyril. Okay. Uklu. Okay. All right. David. Herrera. Yeah. I met you the other day. Okay. Teresa. And Layla is remote. Okay. So almost everybody is here. All right. All right. Now, there's all the stuff in the syllabus. I will talk about the course content in just a little bit afterwards. But so on the syllabus, you'll see course website. So you definitely want to go there. That's where all this information is posted. All the assignments, you have a list of problems will be posted. Any other handouts that I put out for your practice exams. There you two are. So you're coming far from class or something?
Yeah, from Bobby.
Oh, okay. All right, I'll keep that in mind.
I'll have to run here.
What?
I'll have to run.
I guess not. So, okay. All right. Well, I don't want to start class 6 minutes late every time, but
I'll do my best.
okay. All right, and the textbook, you should have gotten an email from me earlier today that has the textbook as a PDF. So I and one of my PhD students wrote the dang textbook. It is really exhausting, 600 plus pages. Those of you who are taking the first course last semester were using it, and I did a ton of work on it since then. And now I think it's pretty much finished and ready to hand in to the publisher. So this is the last semester of it. Anybody will get to use it for free. So not that any of you would, because why would you? But please keep the PDF to yourselves because it is something that is about to go to a publisher. Okay, and then we're only going to use a subset of it, so now we're not going to go through all 600 pages, but yeah. So I'll point out which portions will be of interest in a little bit. Okay, the coursework. So there will be online quizzes posted in Canvas, our learning management system, and the first one I posted already. Then when you go to Canvas, you'll see what quizzes there are and what their due dates will be. This first one is not due for another week. And then that's 10%. 20% comes from problems that are taken from the book. And I've listed the first set of problems on the site. Those are not due until January 30th. There will be a midterm exam, 30%, and then a final exam, 40%. Okay. Now, for a second course in numerical analysis, this is going to be a little unusual because for a number of you here, it is a first course. We had an unusual situation where a number of students in our licensure program were unable to take 460 last semester, but still need an upper level elective. So here you are. What that means is I had to make sure that you guys are able to keep up with things even without the benefit of having taken that class. Now we have people here with a wide range of experience. So we have graduate students, some of whom who have taken numerical analysis before, and then some grad students who have not, or if they have not taken it in a while. And then we have undergrads, some of whom were just in 460 with me last semester, and like I just said, others who were not. So, and I mentioned this because I am very much going to ease into the material. So those of you who are more experienced might be a little bored. I want to get everybody to the same level, so apologies for that, but again, I have to accommodate all 20 people who are in the class. So just hang on, it'll get interesting soon enough. And that's one reason why we're actually going to start with the linear algebra portion of the course, since linear algebra is one of the less threatening of math classes that we have. But numerical linear algebra is a very important part of numerical analysis. And none of that was seen in 460, so it will help everybody get to an equal footing a little faster. Okay, so before I talk about the topics that we're going to see this semester, I need to talk about software. So, this course does have a programming component. One of the things I like about this area is that there's a variety of problems. You'll see some problems where that'll involve proving something. There'll be others where are quite the opposite, where you're writing code to implement numerical methods and see how they behave. So there's some software that is needed for those problems. Now we have MATLAB is what the book is geared around. It's one of the main languages in use in numerical analysis out in the real world. And where you can get it is at mathworks.com. Now, unfortunately, it is not free. The student version is roughly $50, although you are not spending anything on a textbook, so imagine your overall outlay for this course is still going to be less than most math courses. But I will give you a free alternative called octave. Although some people insist on pronouncing it octave, and I have no idea why. Like, have you not heard of a musical octave? I don't get it. And you can obtain that from this site. So that's GNU, G-N-U, like the animal, .org, octave, whatever. So at least that one is free. It has, its language is essentially the same as the language from MATLAB. Whatever differences there may be won't matter to us. I didn't mention it first because I've used it. I don't like it. Its user interface is not really as nice as MATLAB's. You really do get what you pay for. But at least if you prefer, you go ahead and use it. It's up to you. I think students, for the most part, last semester chose to get MATLAB. Now, what we did last semester was to our first homework was about getting up to speed with MATLAB. But because of such the roller coaster of a semester that 460 was, we ended up not covering as much as planned. So one of the chapters that I meant to cover last semester, we're going to see this semester instead. But that means that the semester is kind of full. So for those of you who were not in this class last semester, or if you've not taken any such class in this area before, it is very important that you get on getting whichever one of these you're going to get ASAP. And then what I urge you to do is go to chapter 1. Actually, I'll be more specific. Section 1.2 in the textbook is a MATLAB tutorial. And so there are problems in there that I would recommend working out. I'm open to giving extra credit for doing them. And this applies to everybody. So this is something to make sure that everybody is up to speed on the basics of a language. So this is one reason why I did not make the first homework assignment due for a while, giving until January 30th, so almost 2 weeks. Because those of you who are new to this area, that I want you spending time on homework, which doesn't have very many problems. There's like 7 problems, something like that. And also doing as much of this as you can. Just so when we get to programming problems later in the course, you guys are already up to speed. So it's very important that you fit that in sooner rather than later. And I know this, especially for undergrads, tends to fall on deaf ears, but I'm going to say it anyway. Please come to me for help as needed. Because whether it's coming to my office, which is right there, or contacting me by email or seeing me before or after class, and to get any difficulties straightened out, because I don't want to have a situation where someone falls behind right away, easily preventable. So, programming can be kind of a pain for those who don't have that much experience with it. MATLAB itself is rather unusual, but it's very well suited to working with vectors and matrices, which we'll be doing throughout this entire course. So hopefully that'll make some things a little bit easier. As math majors, do electric majors have to take CSC 101? Oh, okay. And you're probably better off that way. No, I mean that's C++. And MATLAB is nothing like C++. So if anything, if you had taken it, it might cause confusion. So, okay. Now, I mean, just in case you had, MATLAB's language is a very different character. Okay, now, does anyone have any? Does anyone have any questions about the course? Anything from the syllabus or anything? Yes.
Will we need our own computers in the classroom to be able to type code, or is that?
That's actually a pretty good question. Because in the past, I've run this class where it'd be half lectures and half labs, where we'd be down in a different room, but they're taking the computers out of our room, and very messy.
Why'd they do that?
I don't know. Ask Dr. Schroeder. I don't
Are they replacing that?
know.
Just gonna do
oh,
one all classroom?
I think that's going to be like for undergraduate researchers, like where you can work in a group and that sort of thing.
Hmm.
And there's still going to be computers like down the hall in pre-18, but I don't think there'd be enough to accommodate people and enough people in this class. I mean, having 20 people, this is 18 in a room, but
Could we do a projector?
that is something I will do from time to time. If I want to demonstrate something in MATLAB, I would need a projector to do that. I would say that, in general, that would be a good idea, because what I may have to do, instead of having, like before, where I have like some days all lecture and other days all lab, it may be a mix of the two any day. And I know last semester a lot of students did that, or they had MATLAB set up on their laptops and they just go ahead and have them here in class. And I'm just going to trust, I guess I have no choice really, to trust that you guys will be, as I'm demonstrating here on the projector or at the board.
Not on Facebook.
Yeah, that you guys are actually in MATLAB and not in Facebook or whatever it is you guys use now. No. Okay, so, all right, as if I'm any better. Okay, now, okay, any other questions? All right. Now, as far as what are we going to see in this course? Because one of the things that I described about numerical analysis, I remember saying the same thing at the start of last semester, is we're taking various problems that you are familiar with from other courses, but in those other courses, like Math 326, Linear Algebra, or Math 285, Introduction to Differential Equations, you learned analytical techniques, whereas in this course we cover numerical techniques. For certain problems. Now, last semester, the problems that were the main focus were computing derivatives and integrals, and that built on methods for approximating functions by polynomials. So here, in this semester, we're focusing on different problems. So the first problem we're focusing on is systems of linear equations. AX equals B, where A is an n by n matrix, and then x and b are vectors of length n. So, can anyone tell me who, from, for instance, your first linear algebra course, like Math 326, what did you do to solve those kind of problems? What was the process? Does anyone remember? We'll see how rusty you are. So that is a way to describe a solution. It'll turn out it's a very impractical one. How would you get the inverse? They don't- especially undergrads, if you remember how that was done.
Like reduce it into row echelon form.
Yeah, they're using row operations. To reduce to row echelon form. And we are going to revisit that, so we have, so a process we're going to look at very closely is, and it should have been referred to by this term in whatever course you take it, Gaussian elimination, that's reduced to row echelon, or what I'll call it here, upper triangular form. But it's the computer that's going to be carrying this out, not us by hand. You've done that enough. So when it's the computer doing the work, and this is a main theme last semester, will be again this semester, there's issues you have to think of because every arithmetic operation that a computer performs introduces some error. And that's something we're not really going to cover in depth this semester. It was the last semester topic. But we have to try to keep that error in check, not let it grow to unduly large amount, because that error can accumulate so much that the solution that you get, that would be the exact solution if you did it on paper, but now it's going to be an approximate solution. It may be a highly erroneous solution if we're not careful about these things. As an example, when you're working out these problems by hand in your linear algebra course, doing these row operations, most of the time you would be adding a multiple of one row to another row to try to simplify the equation. And sometimes you would have to swap rows. Why would that be necessary? What would go wrong if you didn't?
You have to have the zero first on some of them.
Yeah, because otherwise you might divide by 0. So that still applies, but what we're going to find here is when it's a computer doing it, there are other reasons for interchanging rows that on paper would not come up. Again, to try to reduce the overall amount of error. So that's one thing we're going to look at. Also, for certain kinds of matrices, there are variations on these methods that are more efficient. Efficiency is a key criterion for methods that we look at. Also, to look at a class of methods for solving this kind of system, iterative methods, which is a very active area of research because, for instance, suppose you already have some idea of what a solution is. You'd like to take advantage of that knowledge. Well, Gaussian elimination doesn't let you do that. What if you don't need the solution of high accuracy? Maybe you only want, say, 1% error. Well, you can't stop Gaussian elimination early. You have to see the process through all the way to the end and get high accuracy. Iterative methods are a way to do this. What if most of the entries in your matrix are 0? That actually poses problems for Gaussian elimination because they could introduce new non-zero entries and increase the amount of work. But iterative methods are well designed for these kinds of systems. So there's a lot of reasons to use iterative methods instead of row operations. So we're going to take a look at that. Okay, so that's the first part of a course. So all of this is, okay, so Gaussian elimination is chapter 3. And then iterative methods, we will cover a portion of chapter 5. Okay. All right, so then later on, we're going to look at the next kind of problem, very simple to describe. F of x equals 0, covered in chapter 10. In other words, nonlinear equations. Now, certain nonlinear equations, actually very few nonlinear equations, you know how to solve. You know how to solve a quadratic equation, you can solve any of those. Certain other polynomial equations that work out nicely, you can solve. like if you happen to be able to factor them easily. But most of them, if I just give you any old polynomial equation, you'd be like, I don't know what to do. Well, now you will, because we're going to learn methods for solving these kind of equations. What about equations involving other functions, trigonometric, exponential, logarithmic, rational functions, involving algebraic functions, like involving radicals and so forth. Try to do that on paper, you'd have no idea what to do. But here we'll look at methods that are designed to handle whatever function you give to it. So that'll be the subject of Chapter 10, root finding methods. And some of these methods are surprisingly simple, as we'll find out. But then studying how effective they are and when to choose a particular method over another one, that makes things a bit more challenging. Okay. The rest of the course will be concerned with ordinary differential equations. So we'll look at the kind of problem that you dealt with in your first differential equations course. Y prime is a function of t and y with a initial condition. So this is an IVP, in other words, an initial value problem. So you'd be given an ordinary differential equation here and an initial condition here. So those in your first differential equations course, like in our Math 285, first part of a course was devoted to those kind of problems, and you learned certain methods that only worked in certain situations. And if you got a problem that did not fall into one of those categories, once again, you were out of luck. And that's it. The beauty of numerical analysis is that you're not out of luck. A problem that you have no idea how to proceed by hand, you can throw a numerical method at it and hopefully get an answer. So this is chapter 12, where we'll deal with those kind of problems. And then to conclude, we have second order differential equations. So y double prime depends in some way on your independent variable x and your dependent variables y and also y prime. And instead of an initial condition, you'd be given... Okay, so just found out that recording got interrupted. So I unfortunately had to repeat myself a little bit with what I just written. From here on, this is a 2-point boundary value problem for ordinary differential equations. So that's what we'll be covering at the conclusion of the course. So, and in the process, we'll learn about not just solving a single nonlinear equation, but a system of nonlinear equations that will help us with these boundary value problems. So this is the theme of the course: is how to use numerical methods, how you use a computer to solve problems from linear algebra and differential equations. Because take linear algebra, for instance. You were solving system of linear equations by hand, and how many equations did you work with? Maybe 3 or 4 for a problem on paper, and anything beyond that would be like torture. Well, now the thing is, in real applications, it may be necessary to solve a system of equations that has literally billions, or I think for up to billions now, of equations. So you definitely need a computer to do all the work. And while this is Gaussian elimination is a very general method, there are a lot of problems for which it's definitely not the best choice. And efficiency is essential as well as accuracy. Differential equations, anything you learn in Math 5 would only enable you to solve a very small subset of problems that could be made. And certainly problems that come up in applications, real applications, you won't be able to do much with, so we need another approach. So there are the 3 criteria that we have, and this is what we'll be doing every class, is moving this over here. So, all right, this should work pretty well, I hope. Okay, I just had to make sure not to go too far that way, where you won't see. Okay, all right. We'll go with that. Okay, so criteria. For numerical methods. It's not when you're working out problems on paper where all you want to do is just get the dang answer. So first, most obvious one is accuracy, and you might be thinking, well, duh. But it's not as clear cut as that, because you don't always want the exact answer, because you may have to expend so much effort to get it. How much accuracy do you really need? If you are solving a problem where all the data of a problem, for instance, your initial conditions, things like that, are erroneous, then what's the point of expending more effort to get an exact answer to a problem based on erroneous data? You can just settle for, like I said, something maybe 1% error would be just fine. Okay. So one question is, how much accuracy is needed for a given situation? Second criteria is efficiency. Now, computers are so much more powerful year after year. Whatever computer you have now, it doesn't matter if you got it a week ago, it's already obsolete. And but the thing is, because they're getting so much more powerful, that just means we expect them to do more. And I think, well, because they're so fast, do we really have to care about making every little bit more efficient if they can already perform a zillion operations a second? Well, yes, because problems are only getting larger in scale. Programmers used to be a whole lot more careful in the old days, very old days, as in before even I was born, because they had to be. The school where I went to for undergrad, Purdue University, back in the 60s, they did not have a computer on campus yet. So what they did was they would write the programs on punch cards during the day, and then someone would, like a driver operator, would collect the punch cards at the end of the day from everybody, drive up to the University of Chicago, and run the programs on their computer, gather up all the output, drive back, and deliver the output to everybody in the morning. Imagine if you made a mistake. So now people can afford to be careless, but that doesn't mean it's a good thing. People in those days knew that it was actually more efficient to multiply by 0.5 or 1/2 than to divide by 2. Division is a more expensive operation for a computer than multiplication is. Those kind of details tend to be forgotten these days, but keeping them in mind can actually produce an advantage. Because when you're performing billions of operations, you make them a tiny percentage faster, then it really does make a big difference. So because the problem is so large scale, we have to do what we can. We'll cover methods that will be literally twice as fast as the first method that comes to mind. Well, that matters. And then the third criteria is robustness, or I like to refer to it as reliability. You can have a general purpose method like Gaussian elimination, but for certain problems, it may produce a horribly inaccurate answer. And that because that problem is what we'll describe as ill-conditioned. And when we get to that point, I'll explain what that means. But the general idea is a small change in the problem data could cause a very large change in the solution that's produced. So it means that what if you can't trust that answer? So maybe a different method or different approach of a problem can help with that. So we have to keep that in mind. As I mentioned, every arithmetic operation produces error. If you have a situation where you're subtracting two numbers that are very close to one another, so the result will be very small by comparison, that result will tend to be very erroneous. That's called catastrophic cancellation. That's something that was covered last semester, and something we need to think about this semester as well. As I mentioned back then, it could be literally catastrophic. Failure to take into account cost the lives of American troops in the 1991 Gulf War. And you can look that up. So this is one more thing to pay attention to. That this sometimes the error from each operation can accumulate so much that whatever you've produced may seem to be the right answer, but in fact it's totally useless. So these three things we're going to keep in mind all semester long. Now, another running theme that we're going to have is, for a given problem, like the ones that we have here, what is our approach to developing numerical methods? Methods of producing an approximate solution, whether it's to be carried out by hand or on a computer. Because numerical analysis actually predates the invention of computers. Because for hundreds of years, mathematicians have been trying to find approximate solutions to problems that they could not get exact answers to by hand, even though they were doing everything by hand back then. It's just that once computers were invented, things began to really take off in terms of innovations. And it was like my own advisor, Gene Golub from Stanford, played a very large role in that back in the 60s and 70s. So how to develop numerical methods? There's two good questions to keep in mind as sort of to guide us through a process. First question is, what are the easy problems? All right, so which problems is really obvious what the solution is? There's some sort of category problems. For example, when we're solving equations f of x equals 0, the easiest kind of function to find a root of is a linear function. So we would use that as our starting point and try to build on that. So identifying classes of easy problems is very important. And once we've done that, is there any way that we can reduce general instances of this problem to any of these easy ones? Like going back to this problem of finding the solution of f of x equals 0. Easy to do for a linear function. All right, what if you have a nonlinear function? Then use a tangent line approximation. And that leads to what is called Newton's method. So this is something we'll keep in mind as we go through the whole semester. Now, let's see how much time is at the end. Okay. Oh, we've got half more. So now this takes me to the first real material to cover, which, again, those of you who are more experienced, I might find this too simple, but again, I want to get everybody on the same page, literally and figuratively.
So
So none of that, what you just went over,
What?
the stuff you just went over, that would,
That's like introduction.
okay.
Yeah, it's kind of setting the stage here. Okay. As far as covering something really specific, that's what I'm doing now. All right. I like to have context before I jump in. So, starting our first problem of the semester, solving system of linear equations, ax equals b. Now, we're going to focus at first on direct methods. Those are the kind that you learned in your first linear algebra course, like 326. Fall into the category of direct methods, as opposed to iterative methods that we'll see later. So what we have is the system ax equals b. If I were to write that out, I should mention in the book, I have two appendices at the very end. There's one about a review of calculus, and the other that's a review of linear algebra. For linear algebra one, especially if it's been a while since you've taken a course in that, it'd be a good idea to look at, not necessarily the whole thing, but a good chunk of it to learn your way around matrices and so forth. Especially if what I'm doing here today is unfamiliar to you. So if I were to write out this system of linear equations, I have n linear equations and n unknowns. So my right-hand side values, b is a vector of components b1, b2, up to bn. And then I have my coefficients, my elements of A, multiplying my unknowns, which are my elements of X. Okay. My elements of A, my first index always refers to a row. Second index always refers to the column. So I have here each row refers to one of the equations, first equation, second equation, so on, down to the nth equation. Each column corresponds to an unknown. Notice we have x1 throughout in these first terms, and then x2 throughout in the second terms, and so forth, all the way down to xn throughout in the last term. So column indices correspond to your unknowns, x1, x2, xn. What I have written out here is a matrix vector products. So I have A11, A12, A1n, same for row 2. Multiplied by the vector x1, x2, xn. So this matrix times this vector gives you all of this. Making sure if it's still recording. Yes. Good. Not sure why it went black on me. Okay. And that is then set equal to the vector b, and that describes your linear system. How this multiplication is carried out, again, it's been a while since you've seen this. You go across this row and down this column, so multiplying a11 x1 plus a12 x2 plus, and so on, way down to plus a1n xn, and that gives you everything that's in this first row. And then you do it again for the second row to get the second element, and so on. Again, you want to brush up your linear algebra. if necessary, the appendix at the back of a book can help with that. So I suggest you do that. Okay. Now, the focus for today is which kinds of systems of equations would be considered easy to solve. And because if you just have only one unknown, then that would be a completely trivial equation to solve. So for instance, if it turned out that most of the coefficients in a given row were equal to 0, then these equations would simplify dramatically. So to give an example of a system that's particularly easy to solve, so suppose, what I'll do is I'll specialize this down to a case that's less cumbersome to write out. 3 equations and 3 unknowns. So let's suppose that these coefficients, aij, are equal to 0 if whenever the indices I and j are not equal. So those terms are going to drop out. So for this system that I've just written out here, what is the first equation reduced to? What's left? Yeah, a11x1 is all you have on the left side. You have b1, and then after that, next.
A2,
Yeah.
A3,
Yeah. Okay. What's the solution? X's are unknowns. Okay, so recording cut again. Where I left off, I'd written this far, but these equations are easily solved just by a simple division in each case. The matrix turns out to look like this, where the only non-zero entries are here on the main diagonal. So this is an example of what is called a diagonal system. Unfortunately, I ran out of room in this box here that I've carved out. So a diagonal system is one where all the entries, all coefficients are 0 unless the indices I and j are equal. So we see we have no problem with solution. Now, this goes to one of the homework problems. So if we have a n by n system of equations like this, that is diagonal, then how many arithmetic operations do we need to perform to get the solution? Yeah, n, because we're just going to do one division in each case for a grand total of n division. Okay, so all right, so that simplest case. So if we could reduce the system of general system of equations to diagonal form, then we're home free. We definitely have a solution. But now we're going to step back a little bit. We're not going. We don't need to go that far to get a system that is easily solved. So.
Okay, I have a question. When we write this diagonal matrix, do we need to include the b's on another, like beside it?
Oh, you're thinking of like the augmented matrix? No, because we're just talking only about the matrix. Yeah. And although actually that whole augmented mix thing, we're not doing that. So I will bring it up, but only as to give a reason why we don't do that. Math 326 is the most impractical math class we have. And in other words, the methods that they teach you are all terribly impractical. So I'm here to work past. Okay. Because what if you have several problems to solve, same matrix, different right-hand sides? It'd be crazy to go through the augmented matrix for each one. It's a waste of effort. Okay. Now, let's work with this general 3x3 system here. But now I'm going to impose a different condition. What if Aij is equal to 0 for I strictly greater than j? Now, what's the first equation going to like? Yeah, that's going to be the same. Yeah, that was a trick question. Let's go ahead and write that down. The second equation. Yeah, first term goes away. All right, and finally, so before we had all equations reduced to a trivial form, and we just went ahead. Here, only one equation reduced to that trivial form. This last one. So fine, we'll go ahead and solve it like before, assuming A33 is non-zero. Now, we have x3. How are we going to get x1 and x2? What's the easiest way to do there?
So it's like that.
Yeah, we go ahead and substitute it into the other equations. And in particular, if we substitute it into the second equation, so now we have A22x2 is equal to, if I take this term and move it to the other side, I'll have minus A23x3, which is now known. And now this equation is reduced to that same trivial form. We just have something different on the right-hand side as a result of our substitution. So now we have okay. This is beginning to piss me off. Okay, so we have x3 easily solved. Then once we substitute it in the second equation is similarly trivial solved. And finally, x1. Yes. And so what would happen is if we had a larger system of equations, we would just have more terms like this. Subtracted from the original right-hand side value. Once we subtract them off, then we just have this last division. So this process that I've shown you here is called back substitution. And it's called back substitution because we're working our way through the equations backwards. We will see later forward substitution for different situations. Now, as for the kind of matrix that we have in this case, we have our first row is full. The second row, we have entries only from the diagonal and to the right, and then we only have diagonal entry down here. The last row, zeros everywhere else. So only on or above the main diagonal do we have anything non-zero. This is called upper triangular. Okay. Now, as far as the amount of work involved, we see that each time we compute a new unknown, there's a little bit more work to do. Yeah. So we have, if I were to count the number of arithmetic operations, or in a computer, floating point operations, also known as flops, how how many do we have to perform? Well, here we just have one division. So one flop, or floating point operation. Here we have a multiplication, a subtraction, and a division. So we need 3 flops. And then we have multiplication, subtraction, so 4 operations there. And then a division, so we have a grand total of 5 flops. Okay. Now, from this pattern, we can see that every time we add another unknown, we have like more equations, more unknowns, we're going to add 2 more operations, 2 more flops each time. This will continue 1, 3, 5, 7, 9, 11, and so forth. So the number of flops for the ith equation turns out, in terms of the order that we'll solve them. So I'm referring to this as first, second, third, just so the formulas work out more nicely. I want it to be equal to 1 when I equals 1, 3 when I is equal to 2, and 5 when I is equal to 3. So if I want to have a nice simple formula that expresses how many operations I performed, so I'm generating odd numbers. What should I put here? 2i minus 1. So now if I want to add up the total number of operations, total flops is going to be the sum 1 to n of 2i minus 1. Okay, so let's figure that out. By laws of summations, I can break this up into 2 summations, and then I can pull out the 2 from the first one. Now, what's the sum here? Remember, you're discrete. Wait, let me make sure God, I keep forgetting to turn this thing. Sorry to people who are watching remotely. I suck. Okay. All right. I think you jumped all the way to the answer. Well, I equals 1 to n. That's going to be n times n plus 1 over 2. And then subtracting off this part,
Just one.
n times, so n. Okay, so the 2's cancel. So we have n squared plus n minus n. So it turns out to be, wow, that's kind of freaky. Exactly n squared, floating point operations. Well, here we have 1, 4, 9. So there you go. So we have a bit more work involved. So for a diagonal system, only n arithmetic operations were necessary. Now it's n squared. But what we'll see later is that to solve a general system of equations, it's going to turn out to be n cubed. So this is still a relatively small part of the work. Okay. So this is one thing that we're very interested in is in terms of the size of a problem, an n by n system of n equations, n unknowns, how many operations are necessary? Is it on the order of n or n squared? And when I say order of, we don't really care so much what constant is in front of here unless we have a chance to make it smaller. But so that magnitude of the exponent is of greatest interest. If we have a problem to solve that we can solve it for in order n squared operations rather than n cubed, then we definitely need to do that. So, any questions about how this total number of operations was figured out? So we'll be taking a look at this again for other algorithms later on. Okay, so this is a not as simple system, but one that once reduced to this form, we can go ahead and find a solution. So now, similarly, the matrix A is lower triangular if the ij entry is 0 for I strictly less than j. And for that, you use a similar process called forward substitution, which we'll deal with more later on. Okay, now, so what I refer to here is this upper triangular form. That is enough for us to get the solution. What is that also called from your linear algebra class? It was mentioned earlier today by somebody. Yeah, row echelon form. Okay. Yeah. That's a pure math term, so I don't use that here. Yeah, being a numerical analysis snob. Go me. But you got to admit the term upper triangular is more descriptive. Like echelon, what is that? So it's from pure math snobs. Okay. So now that I'm done trash talking my own colleagues, but okay. So what we're going to concern ourselves with is if we have a general system of equations, something like this, where perhaps none of the entries are 0, and we want to be able to reduce that to upper triangular form and use that substitution. Now, from your first linear algebra class, you have some idea of how to do that. That's what the Gaussian elimination process is for, all those row operations. But we're going to look at those kind of operations from a different point of view, because now, if it's a computer that's doing the work, it needs to do this in a systematic way, also in a way that cuts down on the amount of error that is introduced from every single arithmetic operation. We want to make sure that it is not amplified over time. This leads to the notion of what is called matrix factorization. I can actually factor a general matrix into matrices of a simple form, simpler to work with. But it's one of the main ideas of numerical linear algebra, which is what we're getting into